All right, Descartes' rule of signs and higher degree polynomials, last lesson of the year. So let's first understand what a variation in sign is. So if we have a polynomial with real coefficients and we write it in that standard standard form with descending terms according to their exponents, and we ignore those terms that have coefficients of 0, a variation in sign occurs when the adjacent coefficients have opposite signs. So in this first one, we see we have a change, no change, a change, no change, and a change. So there are 3 variations of signs. It is possible not to have any variation of signs, like the second example. All right, so now let's take that and apply it to Descartes' rule of sign that says if we have a polynomial p of x, the number of positive real zeros or roots is equal to those numbers of variations or that number minus an even whole number. So what we'll do, like in this example, we'll get the 3 and we'll initially subtract off 2. When we end up at 1 or 0, we stop subtracting 2. If it's not possible to subtract 2, then we don't. Then we substitute in a negative x, look for the variations, and do the same thing to get the number of negative possible real zeros. So if we look at this example here, we have one variation in sign of p of x, so we have the one positive real root or 0. When I substitute a negative x in there, I have 1, 2, 3 variations of sign. So I either am going to have 3 negative real zeros or 3 minus 2 negative real zeros. And then in total, I could have 1 plus 1 or 2 real zeros. And then I would take the 1 plus the 3 to get a possible 4 real zeros. Okay, we're going to skip the upper and lower bounds and we're going to go right to example 4. So here I have a nice little flow steps and a flow chart here for you to reference on how we do this process. We're going to apply Descartes first to understand how many and what kind of roots we should be looking at and what are our parameters for the number of zeros. Then we identify whether 1 is a candidate to be a 0 by adding all those coefficients. It does give us a value of 0, so we know that's our first divisor in our synthetic division. We look at this depressed polynomial. We can't factor that, so we go ahead and divide again. We would add them all together just to make sure that 1 would not be a multiplicity of more than 1. And it's not, because these coefficients don't equal 0. So we try -1. And this is a 0. I look at this 4-term cubic, and I'd like to be able to factor that by grouping, but that's not possible here. So I'm going to try -1 again, because it could have a multiplicity of 1, greater than 1. It is 0 a second time. Then I look at this depressed polynomial. It's quadratic, which can be factored. So now I get my 1, 2, 3, 4, 5 zeros that I should have according to the fundamental theorem of algebra. Okay, we're going to do it again with a 4th degree polynomial. We apply Descartes to get 1 positive real 0, 3 negative or 1 negative real 0. We add the coefficients together. +1 is not a 0. We try -1, that doesn't work. -3 doesn't work. +3 doesn't work. -1/3 doesn't work. +1/3 doesn't work. We're like, well, we have exhausted all of our possible rational real zeros, which means we are only looking for irrational zeros. Got it, that's fine.
Do you want any magnetic erasers that just magnetize to your? I have a whole box.
I have some.
Do you? Okay.
Yeah.
Okay.
Thank you for thinking of me. All right, so this doesn't mean there isn't any real roots. There's just no rational roots. What we need to now use is our technology to uncover if these real roots, because we know we're supposed to have 2 or 4 of them. And here we can use either Desmos or our grapher. Here we see here are our 2 real irrational roots. The other 2 are going to be imaginary. Right, here are a couple for you to try. If you can't figure out where these answers came from, then sign yourself up for Compass and I will go through it with you.